The formation of the solar system is a topic that has intrigued scientists for centuries. One of the most widely accepted hypotheses is the nebular hypothesis. This theory suggests that the solar system formed from a giant molecular cloud which collapsed under its own gravity to form the Sun and its surrounding planets. The giant molecular cloud that gave birth to the solar system was roughly 20 parsecs, while the fragments that formed the planets are approximately 1 parsec across. These fragments underwent further collapse, leading to formation of dense cores that were 0.01 to 0.1 parsecs in size. The presolar nebula, one of those collapsing fragments, eventually became the solar system. The composition of the presolar nebula was similar to that of the Sun today, with hydrogen, helium, and trace amounts of lithium forming about 98% of its mass. The remaining 2% of the mass consists of heavier elements that were created by nucleosynthesis in earlier generations of stars. Late in the life of the stars, they ejected heavier elements into the interstellar medium. One or more supernova may have occurred nearby that triggered the formation of the Sun by creating relatively dense region within the cloud, causing these regions to collapse. The highly homogeneous distribution of iron-60 in the solar system points to occurrence of the supernova which injected the iron-60 into the cloud before the accretion of the nebular dust into the planetary bodies. Because only massive short-lived stars produce the supernova, Sun must have formed in a large star-forming region that produced massive stars, possibly similar to the Orion Nebula. As the giant molecular cloud collapsed, it spun faster due to the conservation of the angular momentum. The material within the cloud began to collide with increasing frequency, converting their kinetic energy into heat. The center, where most of the mass collected, became increasingly hotter than the surrounding disk. Over about 100,000 years, the competing forces of gravity, gas pressure, magnetic fields, and rotation caused the contracting nebula to flatten into spinning protoplanetary disk with a diameter of about 200 astronomical units. The protoplanetary disk formed a hot, dense protostar as at its center, the star in which hydrogen fusion has not yet begun. At this point in its evolution, the Sun was thought to have been a T2 star, and it was accompanied by disks of protoplanetary matter with mass of 0.001 to 0.1 solar masses. These disks extended to several hundreds of astronomical units and were rather cool, reaching a surface temperature only about 1000 K at their hottest. Within 50 million years, the temperature and pressure at the core of the Sun became so great that its hydrogen began to fuse, creating an internal source of energy that counteracted the gravitational contraction until the hydrostatic equilibrium was achieved. This marked the Sun's entry into the prime phase of its life, known as main sequence. Main sequence stars derive energy from the fusion of hydrogen into helium in their cores. The Sun remains a main sequence star today. As the early solar system continued to evolve, it eventually drifted away from its siblings in the stellar nursery and continued orbiting the Milky Way center on its own. The Sun likely drifted from its original orbital distance from the center of the galaxy. The chemical history of Sun suggests that it may have formed as much as 3 kPa closer to the galactic core. In conclusion, the nebular hypothesis provides an explanation for the formation of solar system. While it is not without its critics, it remained one of the most widely accepted model for the birth of our solar system. So thank you for watching this video. We hope that you found this information informative and helpful. If you have any questions or comments, please feel free to leave them down below. Don't forget to like and subscribe to our channel for more videos like this, and also don't hesitate to share this video with your friends and family who might find it interesting. Thanks for tuning in, and we'll see you in the next video.